Welcome to Data Science Galaxy. In this video, I'm going to talk about maths behind principal component analysis. I believe you should have a strong foundational level of understanding of mathematics and statistics for you to be able to understand principal component analysis better. Therefore, I'm going to talk about multiple things in this video. I'm going to touch upon the idea of matrices, how the linear transformation is applied using the vectors, and of course, I'm going to talk about the eigenvectors themselves and eigenvalues. Last but not the least, variance and covariance. If you're excited for this, please continue watching till the end and it will be completely worth your while. So what I'm going to do next is to be able to bring some examples to nail down all of these points in an intuitive fashion. Okay, so for that, I'm going to write certain examples and then demonstrate to you how these things works in an intuitive fashion. So allow me to select the pen here and let me just take, and we shall see the idea of linear transformation. Okay, so this I believe you need to have a clear understanding of what I'm talking about when we say the linear transformation. So I'll just explain intuitively. Let us say you have a matrix M when multiplied with a vector V can be represented as some constant represented as lambda multiplied by the same vector. Let me repeat. Whenever you multiply a matrix M with a vector that can be represented as some constant or some number multiplied by the same vector, this vector is what we call the eigenvector. Eigenvector. This lambda, otherwise a constant or a number, is what is called eigenvalue. So you need to have a good level of understanding of these two concepts here. Okay, so let us just spend some time recapitulating what you otherwise know for a vector. What is a vector? Vector gives you both magnitude as well as a direction. For intuitive understanding, here is a popular example that I usually give to people. Let's say you're standing on the ground and throw the ball into the air. What happens to the ball? Ball comes back to the ground, hits the ground, and let's say settles somewhere here. Why is that? That's because of gravitational force. It's very commonsensical understanding, right? Because of gravitation. So if you look at direction of the ball reaching the ground is given by a vector. Along with this, the quantum of the gravitational force, which is, let us say 9.8 meters per second square, is the magnitude of the gravitational force in this direction. So this vector gives you the direction in which the gravitational force is there, and along the direction you have the magnitude of the gravitational force. In this example, it is 9.8 meter per second square. So this is a useful concept for you to understand, to be able to extract maximum variation in a certain direction, and the magnitude or the quantum of the variation gives you the extent of variation extraction possible in that direction. So this is where eigenvector and eigenvalues are useful. There is a bit of historical information. This eigen is a German word. Okay, why they have named it as eigenvector, eigenvalue, I don't have much understanding of it, but it is a German word. You can think of that as simply a vector and a value, useful for understanding principal component analysis. Let us spend some time understanding this, the linear transformation that I'm talking about. I'll go to the next slide and write it one more time. Matrix multiplied by a vector can be represented as some constant multiplied by the same vector. Usually, this matrix, what we take in principal component analysis, is a correlation matrix. I think it's worth noting that. Okay, this is a correlation matrix. So I'm going to explain in an intuitive fashion with an example. What is a matrix? Matrix is simply a grid of numbers. Let us say you have 3, 0, 1, 2. This is 2 by 2 matrix. Matrix is a two-dimensional vector with the rows and columns. 2 rows and 2 columns. Okay, so that's your matrix. I can take a vector like this. Let us say I'm going to take a vector 1, 1. So the dimension of it is 2 rows and 1 column. So this and this are same. The number of columns in the first matrix and number of rows in the second matrix is same. Second matrix is same rather. Therefore, I can do a matrix multiplication. Hope you're all familiar with matrix multiplication. How does this work? How does this work? This row you take and multiply it with the column elements. 3 multiplied by 1 is 3 plus 0 multiplied by 1 is 0. Then you go to the second row, 1 and 2. 1 multiplied with 1 is 1 plus 2 multiplied by 1 is 2. So let us further simplify this. So 3 plus 0 is 3, 1 plus 2 is 3. If I can further simplify this and take 3 out, I can represent this as 1, 1. Okay? So all of you should be able to imagine what I'm doing here, right? Nothing to imagine, you can actually see. So this 1 and 1 is same as the vector here. Okay? So that is the vector that I'm talking about. This value or the constant here is the lambda. So if you notice, I have a matrix which is nothing but the grid of numbers multiplied by certain vector. The resultant output is a constant or a number, in this case 3, multiplied by the same vector. So what does it tell you? Whenever you multiply a matrix with a vector, you can realize the same vector multiplied by some number. So this 1, 1 here is called the eigenvector, and this 3 is called the eigenvalue. This is very, very useful for you to understand principal component analysis. I'm going to bring some variation to this vector that I'm going to make use of for multiplying this matrix with, and you see some of the important concepts to be understood there. So I'll go to the next slide. I'm going to take this same matrix but multiply it with a different vector with some variation. Let me just explain. Let us just take this example of xy coordinates. Okay. For example, this is just for illustration. So we have the origin here. Let us say we have unit 1, unit 2, unit 3 like this. Along the x-axis, let us write unit 1, unit 2, unit 3 along the y-axis. So a point here, if you look at, if I take this, where x-axis is 1 and y-axis 0, it has the coordinates x-axis 1, y-axis 0. A point here, if I take, for which x-coordinate is 0, y-coordinate is 1, we can take it like this. Everybody is clear? So this is one vector. In fact, every point in a n-dimensional space is a vector. That's the reason we should be very clear and critically understanding the vector algebra. So this is 1, 0, and this point here is 0, 1. So let's go back to the same matrix, 3, 0, 1, 2. 3, 0, 1, 2. So this time multiply that with this vector, that means 1, 0. Sorry, 1 and 0. So if you multiply, 3 multiplied by 1 is 3, 0 multiplied by 0 is 0, therefore you get 3. 1 multiplied by 1 is 1, 2 multiplied by 0 is 0, so you get 1. So you get 3 and 1. So if you notice, this is xy coordinates, if you can think of like that. 3 and 1 would be somewhere here. So this point is 3 and 1. Hope everybody is clear. From this origin, if I can write a line joining that point 3, 1 in the coordinate space, something interesting do you notice? What is this? We multiplied a matrix with vector 1, 0, that is this length on the x-axis, but the resultant output is 3, 1, which is nothing but this point. Notice it is not just stretched. The line representing 3, 1 is stretched. All of you should be able to get this. Stretched, and not just that, it is rotated. This is the idea of transformation that I'm talking about. Hope everybody is clear. Okay, it is not just stretched, it is rotated. Important points, stretched and rotated. So moving on, I'll go to the next example where I take same matrix. Instead of 1, 0, we take 0, 1 for the multiplication of the vector. So let's go here and write it one more time. We had here this point 1, 0, and we had this point 0, 1. Take the same matrix. I'll go back and quickly show you 3, 0, 1, 2, 3, 0, 1, 2, and multiply it by 0, 1. So let us just simplify this. 3 multiplied by 0 is 0, 0 multiplied by 1 is 0, 1 multiplied by 0 is 0, 2 multiplied by 1 is 2. So we have 0, 2. 0, 2 would be this point. This is 0, 2. What happened? Unlike the previous case where it is stretched and rotated, here it is only stretched. And notice here it is stretched in the same direction of the vector 0, 1, but not rotated. So I'm going to call it out. Stretched in the same direction, but not rotated. Okay, so it's worth noting these two interesting examples along with the illustration of this linear transformation for you to be able to understand matrix, vectors, and values. I'm going to talk more about variance and covariance in my next video, that is part 2. Hope you liked this video. Hope you liked what you saw. Please upvote it, share it, subscribe to my YouTube channel Data Science Galaxy if you have not already. Thanks for watching. This is Manjunath signing off. Bye bye and happy learning.